So far with LeChatelier's principle, we've talked about if you add a reactant or a product, or you take a product or reactant away, the reaction is going to shift to bring Q back into numerical agreement with K. And then we talked about when you change the volume of a reaction, if you decrease the volume of a container or increase the volume of a container, or add more water or take some water away from a reaction system, again, the reaction will shift. If you decrease the volume, it's going to shift to the side with fewer aqueous particles or gaseous particles. Or if you increase the volume by adding more water or making the volume of the container bigger, it's going to shift to the side with fewer gas particles or aqueous particles. Or excuse me, it's going to shift to the side with more aqueous or gaseous particles. Now, in both of those cases, again, the equilibrium value does not change. The reaction just has to, again, fix itself, basically, to get back to the equilibrium ratios found in the problem. Okay, our third and final situation deals with temperature. Okay, and when you change the temperature of an equilibrium system, that is the time that absolutely the equilibrium constant will change. Okay, so when the temperature changes, that's when the equilibrium constant will change. Okay, so removing or adding products or reactants, compressing or increasing the volume of a container cause shifts to occur, but the equilibrium constant itself doesn't change. However, when the temperature of the reaction changes, the reaction is going to shift to counteract the temperature change. And again, in this case only, the equilibrium constant value will change. Okay, now which way does it shift depends on whether the reaction is exothermic or endothermic. So for example, in the reaction that we saw above, you can see it down there below again, delta H is a negative value, right? That's an exothermic reaction. This one right here, we had seen that delta H is a negative 92. So that is an exothermic reaction, which means that when this happens, when that reaction happens, it's releasing heat. Heat is being released. And since heat is being released, we treat, notice the way we say that. We don't say that heat is a product. We can treat the reaction as if heat were a product, since it's being released from the reaction. So what that does, basically, it means we put heat on the product side. Now, if we put heat on the product side, and now we just treat it like, what if you add a product or take away some product? What if you increase the temperature of that reaction? It's like we've added some product, okay? Because heat is a product, and you increase the temperature, you've added some heat. And we know, what does the reaction do when that happens? The reaction shifts back to the left, okay? If you lower the temperature, you've removed some heat from the reaction. So if you lower the temperature, what's the reaction going to do? It's going to shift to the right to make more of it. And again, the reason that affects the equilibrium constant is because this value gets bigger. When it shifts to the right, this value gets bigger, these values get smaller, and that, of course, is going to change the equilibrium constant value. Okay? If it's an endothermic process, let's say you have a positive delta H, then you put heat on the reactant side. And again, you treat it as if heat were a reactant. And now what happens if you increase the temperature? What have you done? You've added some heat. What does the reaction do? It shifts to the right to balance that out. Okay? If you lower the temperature, what have you done? You've removed some heat. What is the reaction going to do? It's going to shift to the left to make more of that heat. Okay? So, anytime the reaction shifts to the right, when it shifts to the right, you're making more product, you're reducing your reactants, the equilibrium value constant will go up. Anytime the reaction is going to shift to the left, again, only when a temperature change is involved, obviously the products are going to go down, the reactants are going to go up, and what's the equilibrium constant value going to do? Of course it has to go down. Okay? So a couple of other scenarios dealing with LeChatelier's principle. Let's say you have NO plus O2 making NO2, something like that, okay? What if I add a gas that's not involved in the reaction at all? Let's say I add some argon gas, or I add some NO3 gas, which is close to this, but it's not the same. Or what if I add some O3, not O2, O3? What if I add a gas that is not one of the chemicals directly involved in the equation? Okay? Of course, if you add some more gas, what's going to happen? The total pressure in the container is going to increase. Okay? And argon, any noble gas, helium, krypton, any of those noble gases are very commonly used in a situation like that. However, by adding another gas, yes, the total pressure in the container increased, but remember, the kinetic molecular theory says that we pretend like the gases don't take up any space. So by adding argon or NO3 or ozone, that does not affect the partial pressure of the other gases and will not cause a shift in the equilibrium. Okay, but I thought you said when the pressure went up, it shifted to the side with fewer gas particles. That is correct. Only when you change the volume, though. Okay, there's lots of different ways you can change the pressure inside of the container. So when the pressure increases, by them decreasing the volume of the container, that's when it shifts to the side with fewer gas particles. If they just say the pressure goes up, but they don't tell you how, then you have to say that there will not be a shift in the equilibrium because there's not enough information to know what caused that pressure to go up. Is it the fact that you added a gas that isn't involved in the reaction? Maybe you decrease the volume. Maybe you raise the temperature. But there's so many different ways you can increase the pressure inside that container that if they just say the pressure is increased and they don't say how, then you have to say it will not cause a shift in the equilibrium. Typically, they don't do that. Typically, they tell you how they're increasing the pressure. Okay? But in this case, when you add a gas that is not directly involved, even if it's really, really similar, O2 versus O3 is not involved in this reaction. Okay? NO3 is not involved in the reaction. They try to use ones that are really close to make you think, oh, well, maybe it does. Okay? It does not cause the equilibrium to shift in either direction when you add a gas that is not one of the gases or aqueous particles in that solution. Okay? Now, let's look at something like this. Let's say we have A solid plus B gas making C gas. Let's say that I add some C. Okay, I'm going to add some of this to the reaction mixture. Equilibrium here. Okay, what's going to happen? Of course, there's going to be a shift back to the left. Okay, if the question asks you, what happens to the amount of A in that reaction container, if a shift occurs, and it does shift to that side that has the solid in it, the amount of the solid will go up. Okay, because a shift did happen. Okay, so if a shift is going to occur because one of the gases or the aqueous particles changes and it shifts to the side with more that has that solid on it, then absolutely the amount of that solid is going to go up. Okay, and likewise, let's say you add some B to this equation. What's it going to do? It's going to have to shift to the right. What happens to the amount of the solid? The amount of the solid is going to decrease because you have to use that solid to make more of that product. Okay, now, what if I add some solid to that container? If I add some A to that container, what happens? Nothing. Okay, because that's not part of the equilibrium system. So changing an amount of a solid or a liquid in that container does not cause a shift to occur. But if a shift is going to occur either to the right or to the left, the amount of the solid will be affected by that because it just means the reaction is happening. Okay, adding more solid does not make the reaction shift in one way or the other. But again, if a reaction is going to shift and it shifts towards the solid side, yes, the amount of the solid is going to increase. Or if it shifts away from the solid side, yes, the amount of the solid is going to decrease. Okay? So that is something that we have to think about when we're thinking about number 1 there. Okay, and then number 2, this one's pretty easy. A catalyst. What does a catalyst do again? We learned about this in Unit 4. It lowers the activation energy by creating an alternative reaction mechanism. And so what does it do? It increases the rate of the forward and the reverse reaction. However, it does not change the composition of the equilibrium mixture. Okay, remember that a catalyst is something that you start with and then you end with it. So it's not in the overall equation, and so it's not in the equilibrium constant expression. So it increases the rate that you reach equilibrium. So you'll get to equilibrium faster, but again, the ratio of products to reactants is still going to be the same. So the catalyst does not, yes, it makes the reaction reach equilibrium quicker, but it doesn't change the ratio of the reactants to the products in that equilibrium mixture. So the value of the equilibrium constant does not change by the presence of a catalyst, and no shift occurs when a catalyst is added to an equilibrium mixture. What does change? The rate or the speed at which you reach equilibrium. That's it. Okay? So there's 3 main situations with LeChatelier's principle. Adding or removing reactants or products, changing the volume of a container, whether it's a gas or an aqueous solution, and changing the temperature of a solution. Okay, now, of course, these 2 also play a factor, but those are kind of the 3 big ones. Okay, so, and remember, the only time the value of the equilibrium constant changes, and yes, it changes every single time, is when you change the temperature of that solution or that gas chamber, whatever it happens to be in. Other than that, the equilibrium constant doesn't change. Just the value of Q has to come back into numerical agreement with the equilibrium constant.